This is an introduction to phased array ultrasonics, and it's based on advanced technology from Sonotron NDT. We are just presenting here the basics for those people who have the know-how about conventional ultrasonics but don't have the knowledge about phased array technology. Let's first have a look to the history of phased array technology. Actually, there were some scientists in Japan who first used this technology, and in 1960 it was used for medical applications, and in 1970s they managed to display the results in an image like you see on the right. And you see those in this kind of image. This was one of the first images taken, and there were twins. So this was a proof that there are twins on the way. The first instruments were only applied in medical applications because the structure of the bodies did not require high standard for the electronics due to the relative low changes in the density. Electronics for industrial application need to cover a wide range of materials, from low thickness to high thickness, and very, very different sound propagation behavior. Today, most of the instruments are still based on electronics developed for medical systems. In 2009, Sonotron already developed their own electronics, which is much better suited for the requirements of industrial applications. So what are phased array systems? A phased array stands first of all for a higher number of piezoelectric elements which are placed in one housing. The common quantities of those elements are 16, 32 or 64. A special kind of electronics capable of driving the elements in such a way that this cluster of elements generate a resulting ultrasonic wave in a test object, which can be inclined under a certain angle, means under a certain angle, or focused in a certain distance. The probes, also called transducers, with several piezoelectric elements, which might be equipped with a screwable delay line or wedge. And you see down here, this on the left is actually a standard PA probe, phased array probe. And here on front of this probe you can just screw on such a delay line for inspections perpendicular onto the surface. And in case you want to do an inclined inspection, you need to use such kind of wedge. Also, that wedge can be screwed on, and then you can do some inclined inspection like weld inspection and so on. So the probes with several elements, which are placed either lined up in a row or two rows or in a square, so means they can have a different structures. The typical frequencies are between 2 and 10 megahertz. So what is different in phased array in comparison to conventional ultrasonics? You know, when you use conventional ultrasonics, especially for weld inspection, let's say, and you use angular probes with a fixed angle like 45 degree, 60 degree, or 70 degree, and ultrasonic wave which enters into the material is a transversal wave. And here you see a picture about a probe, angular probe, but in this probe the angle has been made, it's rather small, this angle. It's below the so-called critical angle, and when it is below the critical angle, the effect is that you have two waves inside the material. You have the transversal wave and the longitudinal wave. So what has been done for the conventional ultrasonic inspection and the angular probes is the angle here has been increased above the critical angle, which is something like 33 degree, for example 45 degree, or 60, or 70. Those angles are actually the angles inside the material for the transversal wave. So you see in this picture here The longitudinal wave goes up here. It goes inside the wedge. It doesn't go back to the piezo element, so it is not visible on the screen itself. Only the transversal wave is present. And just to explain why this is so important, suppose you have such kind of angular probe where you have two waves and you get a reflection from somewhere, from a flaw. You don't know which one has actually hit this flaw, longitudinal or transversal wave. So you must have one wave to be sure that you have the right distance later on measured, or the depth and so on. All right, now we understand the reason. I think people who have this basic know-how in ultrasonic inspection, they already know it must be above the critical angle, and then usually 45, 60 and 70 degree angles are used. Now why I'm telling about this? Because it's so important, because in phased array you can actually use any kind of angle. You can also put 30 degree there, but if you do that by mistake, you might hit the flaw with a longitudinal wave, and that gives a false indication, or it's not possible to analyze the data. All right, so again, what else is different in phased array in comparison to conventional ultrasonics? In phased array testing, a certain range of angles are used during inspection. Let's say from 37 degree to 75, and in steps of 1 degree. That means we have a beam in 37, 38, 39 and so on, up to 75. So a lot of angles are covered. And here in this picture you see on the right there is a phased array probe, and you see all the beams with different angles, and how the weld is covered with just one probe in one position. You cover the entire weld. So this of course improves the probability of detection very much. Yeah. However, it's essential to choose a range of angles which only propagates in the material in one type of wave, transversal wave. I mentioned that before, so one should make sure that it's above the critical angle, the first one. And why is this so important? I mean, if you want to inspect the weld, and you first start with conventional probes, 45 degree, and you move then forward and backwards, and then you cover the weld with one angle of different distances, of course, yeah. But to make sure that you really have cover more areas, you need to do the same with the 60 degree, also backward and forward, just to see that you have covered a better volume. And you can do that with 70 degree again, and then you have even a better coverage. So when you use a phased array probe, no need of using several types of scan, not to do several types of scans or using different types of probes. One probe is enough. So that's the advantage of a phased array technique. One can say that one PA probe substitutes a high number of conventional probes with different incidence angles. So again, what is different in phased array in comparison to conventional ultrasonics? What else is different? In phased array testing, the probes is guided parallel to the weld along a line. It's so-called line scan, and it's not moved back and forward as in conventional inspection. You see here in the picture, here you move this backward and forward, and then you go further along the weld and inspect it. Yeah, but it's not required when you use the phased array probe. The phased array probe is just placed in a certain distance from the weld, and it's then moved along the weld in the same distance all the time. And that makes it possible to capture all the data, because you can with an encoder find the distance, the movement, the distance, and at every single position you get all the raw data, all the A scans for every single angle. So that's a great advantage. You can use a scanner, which keeps the probe always in the same position, stable, and then capture all the raw data. So how is it possible to generate all the different angles in the phased array probe? Let's look a bit in these details here. Let's take a look at this picture first. In this picture we have only two elements, let's say, which are getting a pulse from the pulsar at the same time. At the same time they get the pulse from the pulsar, and the signal, as you can see, is in phase. That means both have the same, at the same position, the negative amplitude and the positive amplitude. So if you do that for two elements in the probe, in the phased array probe, the effect is that you get a resulting amplitude which is of double high, the double height, yeah? So it's increased amplitude. So two signals in the same phase are adding up to a high amplitude. So that means those individual waves are overlapping each other. And when they overlap each other, you change the timing here, you can create different effects. One effect, for example, you say here, there are two signals which are out of phase. This one receives the pulse over here, the other one has already received the pulse and is now in negative, while this is positive, and at every single point you have to add both values, the negative here, the positive there, and then you see the results here on the top. It's a lower amplitude, a lower resulting amplitude. And what happens when you have an opposite phase, when you have two elements, they receive the pulse from the pulsar completely opposite. That means when this has a positive amplitude, the highest value, this has the negative one, it adds together and it's just a baseline, so they cancel each other out. This is just a concept when you use different sound waves and let them somehow interfere with each other. And you can, when you do that, focus the resulting beam or change the direction of the resulting beam. How you come to that now? How the generation of different sound fields is done. Actually, the piezoelectric elements in the phased array probes are very, very small and therefore cannot produce powerful sound waves. Only if we use several of them simultaneously, then it becomes possible to have a high sound wave with high amplitude. The wave strength is increased, and unlike conventional testing, the size of the piezoelectric element is adjustable in a phased array probe by simply adjusting the simultaneous use of multiple elements. And that is, the selection of multiple elements is called the aperture. It's actually the number of oscillators used or elements used. Yeah, the number of elements used. By suitable time delay control of the individual pulsar driving the elements, both sound beam focusing and an inclined sound beam can be generated. It's just a matter of how to drive the individual elements. If the individual elements are controlled by the electronics of the device in such a way that they generate successively resulting sound waves in a certain angle range, like from 37 to 75 in 1 degree increments, then one speaks of a transmission modulation sequence. It's also called focal law sequence. So, transmission modulation sequence, a focal law, what is this actually? It's a phased array system which has a so-called focal law calculator in the electronics. This device determines the various time delays with which the elements are controlled. The probe and wedge properties, geometry, speed of sound, sound emission point are also taken into account, as well as the geometry and acoustic properties of the material to be tested. The use of the phased array system defines the control sequence of the electronics only by various settings, e.g. angle beam and increment, angle range and increment, in order to generate the desired sound field. So the elements are then electronically controlled in such a way that entire areas, like angle range from 35 to 80 degree, are automatically scanned without moving the probe. You just place the probe and it's electronically moving the angle from 35 to 80. This process runs at a high speed so that the volume can be tested within a short time with many sound angles and or focus depths. And here you see a nice animation for that. Here on the left, the elements are driven in such a way that they actually have a resulting sound beam which is a focused one. You see here the outer ones get the first signal. Now you will see that. The outer ones get the first signal, and then with a certain time delay the inner ones are coming a bit later. So those waves, individual waves, are overlapping each other, and the resulting wave is a wave which is focused in a certain distance. Which means when you key in a different sound, a different focal distance, that actually only means that internally the electronics will make a higher delay here to the sound beam, so that you that the resulting sound beam has a different focal depth. So that's the way of focusing. Here in this case you will see that at first this one is getting the pulse, and then there's a certain delay, a certain fixed delay for all the others, and all those waves are overlapping each other, and the resulting one is a wave which is inclined. As you can see, it's an inclined wave. It goes here under a certain angle. So you can control this angle just by changing the time delay. Now here you have both together. At first you have an inclined portion, and then also you have a certain delay for a focus. So you have a focus under a certain angle. It's a combination of the other two. You see, it's now focusing here in this area. So this is the concept. Why is phased array used? Yeah, of course, phased array systems allow much better probability of detection. It's more comprehensive data capture and documentation. Why? Of course, we use a wide range of angles, so we cover much more of the volume, so the probability of detection is higher, and we capture more data because when we use the scanner, yeah, to capture the distance, and then at every single position we get all the data for all the A scans for every single angle, and we can document that at the end. The test can be performed more complete, of course, higher volume, more complete. At every single position we get all A scan data. It's safer, yes, it's safer because we capture more critical areas or critical flaws, and it's faster because we don't need to do several scans under different angles. Yeah, phased array systems can in many cases replace X-ray inspection. This is especially the case when using the do-it test technology developed by Sonotron Entity, in which phased array and TOF tests are carried out simultaneously. So that means you can actually do a scan where you check with phased array from both sides of the weld simultaneously, and you use also the TOF information You use two TOF probes, or even 4 TOF probes are possible for higher thicknesses. And then you can capture all the data in one shot. Yeah, and then you have the data available, the raw data, and you can do the analysis easily. And one more thing, why it can replace X-ray inspection? The point is, in the past, it was we were always relying on the inspector who does the inspection. Yeah, and so the coupling quality, for example, is one important thing. If the coupling is not sufficient, you don't have a reliable result. And that's why you never had real good documentation when you do ultrasonic inspection. X-ray gives you a picture, and that shows you everything. Of course, some things cannot be seen with X-ray, only seen with phased array or ultrasonics, and the other way around. But due to the fact that you can also monitor the quality of the coupling, it is really possible to replace X-ray in many cases. Phased array systems are potentially more economical to use, and here I put the word potentially because there are so many instruments out there in the market which are very difficult to operate, and it takes a lot of training to get people to a certain level that they can use it properly and calibrate it properly in a reasonable time. So that's one of the weak points, or let's say that was one of the weak points until now. In some cases it still is, but now with the new generations coming, the operational concept has been improved. So, but one has to look at this point, of course. So in general, what are the benefits? Just to repeat, we have a better coverage of the volume to be tested. We have a comprehensive and faster testing, versatile application. There are much more applications that can be covered with phased array compared with conventional ultrasonics. Better probability of detection, potentially more economical test method. One phased array probe replaces many conventional probes. You can also do multiple checks in one shot. For example, it's called multi-group. Multi-group allows you to do inspection simultaneously with a so-called sector scan, where you have a range of angles you cover doing inspection, and at the same time you also do inspection under one particular angle or two particular fixed angles, also possible. And the coupling control, it can be also set and will be stored also, the quality of the coupling. It allows to store a large amount of data and provides therefore better documentation. Yeah, unfortunately many phased array devices in the market are difficult to operate, I mentioned that. So extensive training is necessary to learn how to use and evaluate the results. The Sonotron PA devices are based on the operation of conventional test equipment and represent sound fields and reflections from the material precisely in a true-to-scale illustration of the test specimen. That is called TTGI technology. This makes it much easier to analyze the data. I'm coming to the TTGI later. So influences variables in a phased array inspection. As with conventional tests, the efficiency of the ultrasonic PA test system depends on a large extent on the selection of the probe, the device with its adjustment options, and the acoustic properties of the test material. 4 of the most important parameters for the PA probes are listed below. First of all, the frequency. The frequency affects the near field resolution and the width of the sound field. High frequencies allow for better resolution, better signal-to-noise ratio, and better focus. On the other hand, the sound pressure decreases faster at higher frequencies due to the sound attenuation. Therefore, probes with low frequencies are used for the testing of thick and sound attenuating and sound scattering material. So it's actually the same as with conventional. The frequency, selection of the right frequency is important. The element size, pitch, so-called pitch, Smaller elements improve the resolution capacity. The smallest element size available in PA probe is 0.2 millimeters. So very, very small element. The pitch is rather small. So you need a couple of those to increase the resulting wave so that you can use it properly. Oh, coming to the number of elements. As the number of elements in an array increases, and here array means the total number of piezoelectric elements available in the PA probe. That's the array. When we increase the array and we use all the elements, the possibility to increase and to cover a larger test volume is there. Test sensitivity is better, focusing and angular sound beaming as well. The pitch and aperture. The so-called pitch is the distance from center to center of the individual element. One can actually say the pitch is almost equal to the size of the element. Aperture describes the number of currently used active elements. So that means you can have, for example, an array of 32 elements, but for a particular application you only use an aperture of 16. So that means only 16 are used from the 32 available. Aperture is 16. The larger the aperture, the more accurate it is possible to focus. Most devices on the market support PA probe with 16 and 32 elements. So that means they have 16 or 32 pulses on board. Portable high-performance devices such as those from Sonotron operate in parallel operation. That means there's no multiplexing. There are instruments with multiplexing. They are not so fast because they multiplex. They have, for example, 16 pulses, and then they have 128 receivers. But that means the 16 pulses have to be used several times to make sure that the inspection is made with the high number of receivers. Sonotron instruments have all parallel operation, and there are 32 or 64 elements in one aperture. Sometimes people find that there are some unwanted secondary sound effects on when they use phased array probe. Those things are happening mainly very close to the surface, below the probe. There's some interference reflections close to the sound exit points, and this comes due to the fact that there are some overlaying on some weak sound fields overlays, and that spreads in different directions, and that is somehow unwanted secondary sound effect. And if someone thinks there's a flaw under the surface, directly under the surface, just lift up the probe, and when you still see those signals, then you see it's one of the unwanted secondary sound effects. It's not a big deal. Phased array probe selection. As for conventional probes, the selection of the PA probe is also very important. So one needs to look for the right pitch, the Schwingerweite, it's the German word, it's the elevation. It actually means the width of the element, used aperture, from the array, how many elements you are using, and the frequency, of course, very important. A large number of elements is usually better, but the cost is the critical part here, because when you have an instrument with 64 elements, 64 pulses, it's much more expensive than one with 32 or 16 pulses. A larger pitch achieves a larger overall aperture, but this may lead also to more interference indicators, so this unwanted signals. Let's see, look about the instrument from Sonotron, Isonic 3510. It's a device which has everything on board: phased array, conventional technology, 2 channels, and TOF 2 channels, all in one device. And one can already see here on the screen, you not only see the settings of the instrument, you also see image on the screen which shows you the part under inspection. Conventional technology in Toft. This is on board. Those softwares are on board for the corrosion mapping, for example. Here is one for angular inspection. Another one is quasi C-scan image. I will come to that later. And this is, of course, the Toft software. It's all on board. The one I wanted to show you here is also special software developed for floor map screening. It's a screening tool. Very important to understand. It's only a screening tool, but it helps a lot to give an idea about the condition of those oil tanks, for example. So what is the issue here? You see here, this guy is he puts a probe here on this side, on this area, and it's beaming inside. And this plate is tested for corrosion, and this is the plate down here in this illustration. So the probe is here. There's some sound traveling inside. Then a guided wave runs through. It's reflected from some corrosion, and it gives an indication about the distance of the reflector. So this is the concept, and then you get a quasi C-scan image like this one. Now here's the initial pulse, and then in this direction you get some reflections. For example, if this is a higher corrosion, you get in this case deeper color, black color, for example. It's a matter of how you calibrate the instrument. What you can do is you cannot actually evaluate precisely the depth of the corrosion. You can do some kind of screening, and you can determine whether it's 30%, let's say close to 50 or 70% corrosion depth. That's possible. Here we have the Toft software, and everything required is here for Toft inspection, with 2 channels also, so up to 100 millimeter thickness. Then let's take a look for this TTGI technology. This is unique in the market, and this already shows you what it actually means. You have a test piece here. As you can see, this test piece, a T-joint, and there is a probe over here in a certain distance to the weld. This probe looks like a MWB probe, but in fact it is a phased array probe. We have 16 elements inside here. You see the thick cable here also. There are 16 elements which are controlled by the electronics, and they test the weld somehow. And what you see on the top here is the content on the display. What you see on the display. Of course, you have to key in the thickness of this part. You have to define the weld somehow. You can also, by the way, define the weld preparation if you want. It's also shown here, I mean, not in this case, but it can be done. The front edge of the probe is here, the 0 point, which is marked here. So when you move the probe here parallel to the weld in that direction, from here to there, you inspect the whole volume. Whatever is blue here is the area which has been covered during the scan, or which is covered during the scan. And if there is a reflection, a flaw, you get an indication here. And you see it's a range from the lower angle, which actually reflects from the back wall up here. Higher angles reflect up here, and those high angles go straight through. This area is not inspected. Here this area is not inspected, but this is inspected. So it's very easy for the operator to see what he does, where he is in the test piece, on the test piece, and what he is actually covering during the inspection. Some explanation about this technology. Let's say we have a probe, a phased array probe over here on a test piece, and we have this sector. So we run with a range from a small angle to a high angle, and we have a particular angle where we hit a side drill hole. We get a reflection from that side drill hole, and that's the one, the probe, or the flaw 1 we see over here. Under a different angle we get a reflection indirectly, because there's a reflection from the back wall to the side drill hole and back. So we get another indication on the screen. So we have a sector scan at the end with 2 indications. But both indications are from the same flaw. That's easy to understand for an operator when he just has this one reflector somehow. It's easy. But when the geometry is a bit different, like here in this case, where we also have the same probe here again, and we have 3 reflectors. We have a side drill hole, we have an edge here, and we have the end of the saw cart over here. So we must get 3 reflections. In a normal sector scan we see those reflections, but it's a bit hard to understand which one is what, This one is actually from the edge, okay, but it requires some understanding and some experience to evaluate those results from the sector scan. But when you use the particular software from Sonotron, it becomes easy, because you key in all the data, the dimensions, you define where the probe is, the 0 point here, and then you know what is covered, where the sound beam is going, and you see in live doing the scan in the image on the screen, you see the reflections here. You see reflections from the edge, the geometry echo, you see, let's say, the floor echo, and you see the end of the socket. Of course, only the end, because other sound will just travel up, not going back to the probe. So that makes it very easy to evaluate. Here you see a typical sector scan of a weld. Not so easy to interpret. But here on the right you see how it is in the Sonotron software. When you use that software, you again key in the data thickness, the weld preparation, and so on, and you see the reflections, and you already see that this reflection, for example, is coming here from the top of the weld, so it's a geometry echo, and the other one is coming from here. Maybe a small flaw over here and some small flaws here. And there's a white area. It's also important to understand. In Sonotron, it is automatically filtering out all reflections here from the root, because the root is not a clean surface. You don't know where sound beams are reflected when it comes into the root. It can go everywhere, in all directions, and therefore all reflections from here are filtered out. They are not shown in this image, so you do not see this false indication if there are some in the wrong direction. That's why we have a white area here. Alright, special advantages and unique selling points of the Sonotron phased array devices. Easiest operation. That means we actually have a menu concept which is very, very similar to a digital flaw detector. Almost 80% of the functions are identical, so you can operate it like a digital flaw detector. Only 2, 3, 4 different things have to be added when you do a phased array inspection. Ultrasonic hardware is of the latest technology. It's specially developed for NDT applications, not based on medical technology. We have a pulsar voltage which is up to 300 volts. Amplification is 100 dB analog. It's analog. Very important to understand, because others have maybe 120 dB, but 60 dB is analog and the other 60 dB is digital. And digital means you increase the signal and the noise, so it's not really helpful to have digital amplification. We have 100 dB analog because there are two parts of pulses working. Individual frequency filters and many other things are special here. We have very easy evaluation due to the fact that we use the TTGI technology, because we see in the illustration, we see the component, the geometry of the component. We see immediately where we have geometry echoes, where the flow echoes are, and that all can be seen live, but also it's also captured and can be put in the post-processing, can be seen one by one, every single millimeter, for example, and even for complex components. Yeah, what you can also do is when you do the post-processing, the evaluation later on, you can change certain settings. Yeah, because for example, the instrument capable of capturing 200% screen height. That means you can even later on change the gain settings, and you do not miss anything or do not have any loss of data here. It's all there because we capture all the raw data. Then you have advanced representation, not only A, B, and C images, also 3D images are seen, also for complex components. And then not only in the post-processing part, on the instrument itself you can see results in 3D. And finally, you can do the recording of coupling quality during weld inspection. And that I find this very, very important, because this makes sure that we are not longer depending on the operator itself. The operator, if the operator does some mistakes with the coupling, he will immediately see it and he can correct it by going back and scanning that area again. And if he doesn't do it, it's already stored, and that means you can see it later on that it was not perfectly done with the perfect coupling. So, alright, if you have any questions, do not hesitate to contact us.